Okay, this is number 52 on page 267. At the sun's surface, the gravitational force between the sun and a 5 kilogram mass of hot gas has a magnitude of 1,370 newtons. Assuming the sun is spherical, what is the sun's mean radius? Now, a lot of people are getting the equation on this mixed up. I think the key words here are gravitational force. I think that is our key word. That tells me that the equation actually for this is F G, that's force of gravity, which we normally find by just saying mass times G, m times G. But when you're far away from the Earth or on someplace else, then you have to use this other form called Newton's universal law of gravitation, which is big G, m1 times m2 over r squared, where r is the distance between the two masses. M is the mass in kilograms of the first object, M2 is the mass of the second object in kilograms, and G is a constant. G is equal to 6.67 times 10 to the negative 11th newtons times kilograms squared per meter squared. Actually, reverse that. Newtons times meter squared per kilogram squared. There we go. That's correct. That's big G. All right? Now, if we just look at this idea here, what we basically have is the sun. All right? We have the sun. If I can get the sun to look right here. And the sun. All right? And then we have this hot cloud of gas on the surface of the sun, all right? This is not drawn to proportion. The sun's going to be much bigger. We know this right here is 5 kilograms, and then if you look, we're not given the mass of the sun. Well, we have to look that up in the book, and I think it's in F. It's Appendix F on page 868. And if we look in there, it tells us the mass of the sun. Here it is. So the mass of the sun is 1.99 times 10 to the 30th kilograms. So there's my numbers that I'm looking for, and I'm wanting to know what's the distance from here to there. R. That's the question they ask us, all right? So if I just rewrite this so it has the proper letters, it's going to be mass of the sun times mass of the gas cloud, all right, times big G over R squared. I'm looking for R squared, so I'm going to put my numbers in now. My numbers are, let me get this out of the way, 1370 newtons equals, now we're going to write this one, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times 5 kilograms times 1.99 times 10 to the 30th kilograms all over R squared. And so all I'm going to do is I'm going to switch these two numbers here. This number here, which is a letter, the unknown, is going to be switched with that. And I'm going to put this in my calculator and get a number. And if I just look here, then this top, when I put this top, this part right here, when I put this in my calculator, and hit enter, I'm going to get, at least this is what I got, 6.64 times 10 to the 20th, and that's going to be newtons times meters squared, because kilograms divide out. This divides out with those two, over 1370, and that's going to equal r squared. Do not forget the squared. So I'm going to divide this number by 1370. When I do that, I get r squared equals the square root, take the square root of both sides, right, of 4.844 times 10 to the 17th. See, this is newtons here, so that divides out, and I'm left with meters squared here. Square root of meters squared is meters. So I'll take the square root of that number, and I get the answer that the mean radius of the sun is. We'll put this in scientific notation. 6.96 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8th. I counted 8 decimal places. 10 to the 8th meters. And if you look in the book, on page 267, number 52, the answer is 6.96 times 10 to the 8th meters. And that's exactly it.